Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you very much for the mic is on, I suppose, right? Thank you very much for the very kind introduction. Okay, so the talk I'm going to give today is has a title: Bats Coding for a Network-Coded Fountain. Okay, so we're going to first talk about the problem. Now, in this picture, we show a network with packets generated at the source node S, okay, being multicast to two signals T1 and T2. Well, this setup has nothing to do specifically with the butterfly network, but we're using it anyway. So here we see packets in green and red, where the green packets are those packets that successfully arrive at the destination, and the red ones are those that got dropped along the way. Okay, so we are talking about sending out files which are relatively big, for example, like 20 megabytes consisting of about 20,000 packets. Okay, so we'd like to find a practical solution to this problem, which such that it has low computational and storage cost. Storage cost refers to the amount of storage that you need at the intermediate nodes, and we want one with a high transmission rate and also with a small protocol overhead. Okay, so one possibility to do this is through TCP. Okay, by doing so, you need to do acknowledgement hop by hop, which is not scalable for multicast. Okay, and it mainly because the cost of feedback is too high. Okay, we can also consider using some well-known fault error correction scheme, such as the fountain codes. Okay, it's very scalable for multicast because you don't need to feedbacks every so often, and so therefore, in the case of multicast, it can be implemented quite efficiently. Okay. This is the regarding the complexity of fountain codes with routing, which is in fact extremely efficient. So we consider a file consisting of k packets here. Okay, so remember this notation k. K is an important parameter in this problem. Okay, we've got a file consisting of k packets, and for each packet it consists of t symbols. Okay, so t is pretty much a constant. Okay. So if, for fountain code, the coding is extremely efficient because it uses a kind of sparse coding. It's O of t per packet, which means that the encoding complexity does not depend on the file size at all. Okay? Whenever you don't see a k, it's something good. Okay. Now for decoding, it uses a belief propagation decoding. Again, is a constant. Okay, which does not depend on the file size. And routing in between is a very simple operation, and you need only a very small buffer for that. Now this picture shows how things work. Okay, so on the top are the input packets or the source packets. Okay, and there we go. Okay, so at the top are the source packets, and there's an encoder S here, which encodes them into different encoder packets, and this sent to the source node, sent to the intermediate node U, and what it does is nothing but a store and forward. And along the way, there's some red packets that are being lost. Now, at the decoder at the receiving end T, it employs a belief propagation decoder so that it doesn't have to receive all the packets. As long as it receives enough packets, it can start decoding properly, and at the end you would be able to recover all these source packets. Okay. However, there's a drawback with using fountain code as is. Now let's consider this case when we try to send things from S to T through U, and these links have a packet drop rate equal to 0.2. I was told that in LTE, this is not something too uncommon to happen because the rate is so high. Now for this network, the capacity is equal to 0.8. The reason is that suppose you can you send a file from S to U, okay, because the packet rate is equal to 0.2. You can set it by using a forward error correction like a file encode or TCP. Okay, you can send things from S to U at rate equal to 0.8. Then you can decode the whole file, and then you re-encode and you send it on another link with again with packet drop rate equal to 0.2. Okay, so by doing so, you're repeating what you're doing at U is just to repeat what you do at S. Okay, so by doing so, you actually can send things from S to U at rate equal to 0.8. But this is not the way I've shown you. It's not necessarily the best thing to do. Now, if you apply forwarding, okay, and retransmission end to end for a file encode, the maximum rate that you get is only 0.64. The reason is that this guy does nothing but forwarding the packets that it receives. So from here to here, you lose 20%, so you get 80% remaining. And from here to here, you lose another 20%, so you get a maximum rate equal to 0.64. This is for both retransmission and also for file encodes. Okay, so what file encode buys you is not the rate, but it's the efficiency. Okay. Now, this is the theoretical upper limit for the rate that can be achieved by a file encode. But in reality, if you work with file encode with a small field size, then there's actually a gap between this upper bound and the real rate that you can actually achieve. Now, I mentioned that in principle you can get a rate equal to 0.8 by sending the file here, decode, and then re-encode. Okay. Now there are two problems with this implementation. First of all, there's a delay incurred because you have to decode before you re-encode it, which means that you have to wait until the whole file comes. And if you have a multi-hop network, then every hop you incur a delay, which is not something very desirable. And also that this node has to store all the packets before you can encode, which means that the buffer size required at the intermediate nodes grows with the file size, which is also something not good to have. Okay, now we know that if you apply random linear network coding at node U, in principle you can achieve rate equal to 0.8. Now by random linear network coding, I mean the following. You have a buffer at node U, and this implementation actually is the same thing as the avalanche system that was invented by the Microsoft people at Cambridge. So what you do is that you have a buffer here that stores all the packets that arrives at node U, and whenever you send out a packet, you just take a random linear combination of whatever you have on hand. Okay, even if there's no new arrival packets, next time you send out another packet, you take a different random linear combination. Okay, so there's no delay incurred at all. It's just pipelining. Okay. However, if you apply okay, before I tell you the drawbacks of this straightforward implementation of network coding, I'll try to convince you that with random linear network coding, you actually can achieve rate equal to 0.8. Now, this picture actually shows the operation of random linear network coding. So the first row is the row representing node S. Okay, the middle row representing node U, and the last row representing node T. So if you go horizontally, this represents time. So this node here is node S at t equals 0, t equals 1, t equals 2, so on and so forth. Same thing for node U, t equals 0, node U, t equals 1, so on and so forth. Now here we have some red arrows. Okay, these arrows represents the transmission from node S to node U every time unit. Okay, and it has capacity equal to 1. And there are crosses here once in a while representing the packet drop rate. Okay? On the average, you lose about 20%. Now the same thing from the U layer to the T layer. Okay, again we have packet drops here and there. Now there is also another kind of arrows in black that goes horizontally. Okay. Now this represents the memory from the past. Okay, because we buffer everything and we assume that you remember things in the past. Okay, and for the sake of convenience, we assume that this link has capacity infinity, but in reality, it doesn't have to be larger than a file size. Okay. Now because we have you think of these as water pipes. Okay, and then you try to pump water in at node S at time equals 0. And you want to know, how much water you can get at the bottom layer, okay, as time goes by. Now, because 20% of these pipes are broken, you can press water down from what I think is better to assume that these pipes are blocked instead of the pipes being broken, because for a broken pipe you lose the water. Okay, for this discussion, we think of these pipes being blocked. Okay, so because 20% of these pipes are blocked, you can press water down from the top layer to the middle layer at rate equal to 0.8. Okay, now you can also press water down from the middle layer to the bottom layer at rate equal to 0.8. Okay, because about 20% of these pipes are blocked. The question is whether you can press water down from the top layer to the bottom layer at rate equal to 0.8. Now, the reason why it can be done is because of the existence of these thick pipes that goes horizontally. The thing is that you press water down from the middle layer to the bottom layer at rate equal to 0.8, and the water can travel horizontally and find their way down to the bottom layer. Okay. Now, if we examine one of these nodes in the middle layer carefully, okay, so it has two input links. One is the link from the past, and another input link is the link that you receive the new packets. Okay, so what you do is that by applying random linear network coding, what you do is that you take a random linear combination of the past and the newly arrival packets, and then you send out a new packet. So this picture, this time parameterized graph, or you want to call it a trellis diagram, depicts precisely what the avalanche system is doing. Okay, so in random linear network coding, all we care about is the maximum flow. So now we've seen that the maximum flow rate, actually the maximum flow from S to the bottom layer actually grows with time at rate equal to 0.8. That's why we can, with linear network coding at node U, you actually can send information from S to T at rate equal to 0.8. Okay, this is the intuitive explanation why random linear network coding would do the job. Okay, however, you sacrifice for efficiency, because the reason why Finite codes are so efficient is that the encoding is very, very sparse. Okay, whereas for random linear network coding, which is depicted here, okay, you just take this packet is formed by taking random linear combination of whatever you have, and this is a dense encoding. Again, when you do a random linear network coding at the intermediate node, it is again dense encoding, so that you can still decode, but decoding is not efficient. In particular, the encoding complexity is O of tk per packet. Okay, as I told you, the k is the size of the file, and this thing that as long as k turns up, it's not something good. Okay, we don't want that. For decoding, if you use straightforward Gaussian elimination, the complexity is O of k squared plus tk per packet. So essentially, t is a constant, so essentially it's k squared. Again, it's not something very desirable. So for the intermediate node, if you apply network coding, again, there's some complexity associated with it. And for this straightforward implementation, it requires you to buffer all the k packets, which is essentially the whole file. And this, so if you want to transmit a bigger file, then you require the intermediate nodes to have a bigger buffer, which is something not very desirable either. Okay, so after seeing these slides, we come up with a quick summary. on the one hand, we can have a routing plus fine encode, which is low complexity, but the rate is also not satisfactory. If you want to have a high rate, you can go for network coding, but the complexity is high. So let us first review some existing schemes to try to tackle the problem. Okay. Now, the very reason why applying random linear network coding in the middle node would screw things up is that network coding changes the degree distribution of the received packets. Now, in designing a fine code, choosing the right degree distribution is the main thing. Okay, if you do randomization in between, you screw up the degree distribution, and so low decoding complexity cannot be guaranteed. Okay. So there have been some efforts in trying to get around the problem. Okay, the main idea is to try to tweak the random linear network coding at the intermediate node so that end to end it still looks like a founding code. Okay, but this is something rather ad hoc and it's very hard to extend beyond a very simple network. Okay. But even if you do that, at the intermediate nodes, the computational cost is still high, and you also need to store all the K packets. Okay, and then there has been some work coming from this group. Actually, it's quite a while ago, almost 10 years ago. You guys really know what problems are important. Okay, so the idea is to use so-called chunks to reduce the coding complexity. Okay, so we know that the coding complexity grows at a rate higher than linear, but as long as you keep things small, then things are still manageable. Okay, with if you chop things up into chunks so that you do random linear coding within this chunk here and also within this chunk here. Okay, here you see that the first node depends only on the first node, the second node depends on the first node, and the second node, this is a kind of causality constraint on the coding. Okay, so the idea is to keep things small. Okay, if you do that, the encoding complexity is O of TKL, where L is the chunk size. Okay, the K is still there. And decoding complexity is O of K L squared plus TKL. This is a little better because previously we have K squared, but here it's only sort of linear with K, where we can regard T and L essentially as constant. Okay, but how about buffer requirement in the intermediate nodes? Okay, it really depends on the implementation. But one big problem with using the chunk approach is how to transmit the chunks. Okay, so there have been different approaches. The obvious approach is to do sequential scheduling of chunks, which means that I transmit things for this chunk and I wait until everybody are done with this, and then I move on to the second chunk. But one drawback of this scheduling is that it's not scalable for multicast, because for multicast there could be some many receivers, and some can be faster, some can be slower. Okay, so it's not really scalable for multicast. Another approach is to use random scheduling of chunks, meaning that I have all these chunks and I randomly pick one to transmit, and hopefully this is a new one to you. Now, with this implementation, however, the intermediate node again have to cache all the K packets. Okay, unlike sequential scheduling. For sequential scheduling, you don't have to cache all the K packets. Now, however, such a scheme would become less efficient when a major fraction of all the chunks have been decoded. The thing is that if there are 100 chunks and you already have received 90 of them, if I randomly pick one, then 90% of the time it would be a redundant chunk for you. Okay. Okay, and there has also been efforts along the line of overlap chunks. Okay, the chunks are not totally independent of each other, but this can improve the throughput of random scheduling, but still it cannot reduce the buffer size. Okay. So, what we learned from all this discussion is that Foreign codes are not really compatible with narrow coding, but ratelessness is a good property that we want in the multicast application. Chunks can be used for narrow coding, but are difficult to schedule. So we are trying to address all these issues using a new approach, which we call batch code. Batch code refers to batched sparse codes. Okay, and the operation of batch code is shown in this picture here. So on the top, again, we have all these source packets, and we organize the encoded packets into what we call chunks. Okay, in this case, I'm sorry, it's a batch. Okay, a batch is different from a chunk in the sense that for chunks we kind of think of them as operating independently, but as we are going to see, a batch actually operate with each other. Okay. So here a batch has size equal to 3, and so let's see how we form the first batch. Okay, let's see how we form the first packet in the first batch. Now, to form the first packet in the first batch, we draw a degree distribution. Okay, we draw a degree from a degree distribution, and let's say the degree is equal to 4, and then we randomly pick 4 of these source packets. So let's say we pick this one, this one, this one, and this one. Okay. So what we do is we take a random linear combination of these 4 source packets to form the first packet for the first batch. Okay. And to form the second packet of the first batch, we stick with the same subset of source packets, but we take a different random linear combination. Okay, so on and so forth. So we're done with the first batch. Now to form the second batch, we draw another degree from the degree distribution, and this time let's say the degree is equal to 1, 2, 3, 4, 5. Okay, and then we randomly pick 5 of the input of the 5 of the source packets and form a random linear combination to form the first packet here. Now to form the second packet here, we use the same 5 source packets, but use a different random linear combination. Okay, so it goes on like this, and then we at the intermediate nodes, there can be more than one, but here I show only one. You do random linear encoding, but only within the same batch. Okay. All right. So this picture gives a little more detail of the operation. So first you obtain a degree d by sampling a certain degree distribution psi, and then you pick d distinct input packets randomly, okay, as I said, and then you generate a batch of m coded packets using the d packets. So m is the size, capital M is the size of a batch. Okay, so these here we form the batches x1, x2, x3, x4, so on and so forth. Here are the details. So xi is the ith batch, and so the degree that we use for the batch xi is equal to di. Okay, and the packets bi1, bi2 up to bidi are the packets involved in forming the ith batch. Okay, and then you multiply this by to a generator matrix gi, and then you form this ith batch equal to bi, which is this row vector times gi. Okay. A question?
So the size of the batch is always the same.
They're always the same, yeah. It's capital M.
Okay. So alternatively, I could imagine that if you keep the ratio constant, like it's always like alpha times d.
Alpha times.
So when you choose the degree d, right, and you say that keep the batch size like constant multiplied by.
Actually, it is a good idea to keep the batch size small, as we are going to see. Okay, so we form these batches, and okay, maybe I can go back to this picture and try to explain a little bit more. So this coding scheme actually can be understood as an outer code, okay, here, which is kind of like a matrix generalization of a function code. And then there's an inner code here. And inner code are the random linear network coding applied within the network within each batch. You don't do cross-batch random linear network coding. Okay, so you form these batches, and they're sent through the network, which can do arbitrary linear network coding. It doesn't matter as long as things are linear. And then you get batches out as y1, y2, y3, so on and so forth, where yi is equal to xi, the input batch into the network, multiplied by hi, where hi is the transfer matrix that it goes through within the network. Okay. Now, because we don't do cross-batch linear network coding, yi only depends on xi, but not other batches. Okay. That's why that's how you keep the structure of the outer code intact. Okay, even though if you do random linear network coding within the network. Okay, so the end-to-end effect is the following. On the top we have these input packets, and on the bottom we have some check nodes characterized by the matrices gi, hi. Okay, so in the if you're familiar with belief propagation in function code, what they do is that you find a check node with degree 1, and then you start propagating. Okay. Now in this case, we instead of doing the same thing, we look for a check node I with degree I equal to the rank of gi hi. For example, for this check node here, suppose the degree is equal to 2. Suppose the rank is also equal to 2, then you can decode B1 and B3, and you can start propagating. Okay. So specifically the linear equation associated with the check node is yi is equal to bi, which is bi is the vector of all the packets that are involved in batch I, and you multiply by gi times hi. Gi is the generator matrix, and hi is the transfer matrix in the network. Okay, so you can also apply the technique of precoding as in the Raptor codes. Okay, so the idea is that you precode by a fixed rate erasure correction code. So these are the source packets. You expand it into a larger number of packets by an erasure code, and when you do the belief propagation here, upon being able to decode a fraction 1 minus eta of all these packets, you would be able to recover the original source packets by means of the erasure code. So this actually can give you a higher rate and also lower complexity. Okay. So we need a degree distribution size such that the belief propagation can decode successfully with high probability. The encoding-decoding complexity is low, and the coding rate is high. So I'm not going to get into the details of this asymptotic optimization program. All I want to say is that this optimization actually has to do with the expected rank distribution of the transfer matrix H. Okay, it does not depend on the details of this transfer matrix H, but it does depend on the rank distribution. Okay, and then one can do some optimization accordingly. And this is the complexity of sequential scheduling of these batches. Now, so you may ask, just a moment ago we said that sequential scheduling is not efficient because it's not scalable for multicasting. Then why do we use sequential scheduling here? Now, the reason why sequential scheduling was not efficient for chunk-based random linear network coding is because you need to as a receiver, you need to receive every chunk. Okay, if you cannot receive it, you have to wait until you receive it before you can move on to the next chunk. But for batch code, because it has a kind of like a matrix Founding code as an outer code, you actually don't have to receive all the batches. You only have to receive a sufficient number of batches, and then you can start the belief propagation decoding. Okay? So the result is that the source node encoding complexity is O of Tm. Okay, m is the batch size. Okay, and so these two are constants. It doesn't depend on k. Okay, destination node decoding O of m squared plus Tm. Again, it doesn't depend on k. Okay, so no matter how large your file is, the encoding and decoding complexity remains constant. Okay. Now for the intermediate node, for this particular configuration, okay, which I will elaborate a little bit. Okay, this particular configuration is such that from the source to all these signals, it has a tree structure. Okay, so that the packets cannot overtake each other. I'm going to elaborate further why this is important. Okay. The buffer size only needs to be O of Tm. Okay, again, it's independent of the file size. And for the network coding operation, the complexity is O of Tm per packet. Okay. So yes.
I thought last time when you were giving complexity numbers, the reason you had k was because it was the complexity for the decoding the entire file.
Oh, actually, I clarified with my postdoc last night. In fact, the slide you saw last time, it had a k in it. It is for the total complexity.
Right.
Okay, but now I talk about the complexity per packet.
Okay.
Yeah.
So if you made this for total file complexity, you'd have a k in there.
Yes, of course. Yeah, you have to decode a larger file, you need to work harder. But per packet, it is at least for per packet, you don't have to work harder.
Yeah.
Okay, so T you pretty much can forget about it. It's just the length of a packet that doesn't change. So K is the number of packets that depends on the file size, and M is a parameter to choose. Okay, is a batch size. Okay. So the one thing I would like to mention is that the optimal value of theta is almost the same thing as the rate of the code, which is very close to expectation of the rank of h. Okay, so this is when you have only one hop, then the rank of h is just corresponds to the erasure probability. Okay, when you have multiple hops, then this is what you have to look at. Okay, it can be proved that when expectation, the optimal value theta it can be proved to be exactly equal to expectation of rank of k when expectation of rank of k is equal to m, which is the batch size times probability of rank of k equal rank of h is equal to m. Okay. Okay, so let's go back to this example with packet loss equal to 0.2. So here we apply, batch code at node S, okay, which encodes k packets, and node U actually only needs to cache one batch. The reason is that from S to T, there's only one path, and so the packets cannot overtake each other. So for at node U, you only need to store one batch. As long as you see packets from a new batch coming in, you know that the old batch is over, and then you can just throw away everything, right? And node T only needs to send one feedback after a successful decoding. Okay, so here are some parameters that we obtain by simulation, and here I want to note that we have not applied the pre-coding techniques yet. Okay, if you apply the pre-coding techniques, then the number would look even better. So here K is the file size, okay, 16,000, 32,000, 64,000. And Q is the size of the finite field. Okay, for Q is equal to 2, this is binary. This is for Q is equal to 4 is a very small finite field. And here we choose batch size equal to 32. Okay. And as we see on the lower right corner, okay, the rate can already exceed 0.64, which is the theoretical upper bound on the rate of a finite code, which actually cannot be achieved with a small finite field for finite code in any case. Okay. So things looks pretty encouraging. Okay. And in fact, from the theoretical point of view, what we have obtained is actually a framework which, on the one extreme, encompasses raptor codes or the Founding code of that family. Okay, when m is equal to 1, when the batch size is equal to 1. Okay, then batch code degenerates to Founding codes, and which has low complexity, but it doesn't enjoy the benefit of network coding. Okay. On the other extreme, when you take m equals k, which is the whole file, and degree is also equal to k. That is, you take random linear combination of all the packets in the source file. Then batch code becomes full-fledged random linear network coding, which has high complexity, but at the same time, it enjoys the full benefit of network coding. And somewhere between, we are trying to choose some parameters such that it performs well, and at the same time, the efficiency or complexity is low. Okay, that's what we are trying to do. Okay, so let's talk about some recent developments. So the one thing I would like to mention is that there's one. Yes.
About this code?
Yeah.
So can you flip back? So this discussion is about, the specific code is showing the performance is about 1 hop. 2 hop.
Yeah.
Right. So if I have multiple hop, how the code performance?
Oh, yeah, the more hops you have, the better it is. Because if you have packet loss, then you lose packet along the way. I mean, and if you don't do anything in between it, then you keep losing packet.
The sense of, you say the performance better is compared with just basically just
routing. Compare with routing. Yeah.
I'm also basically compare with random linear code.
It cannot beat, in terms of the rate, it cannot beat a random linear network coding. But
of course.
Yeah.
But how much is the performance gap to the random linear code changes when you have multiple hop?
Okay.
So for example, your example
for batch code, okay,
yeah.
That's something we are in the process of investigating. Okay, so we need to do much more simulation to see how it actually works in the real environment.
It seemed like 0.68 or was it? It should be like 0.8.
It should be close to 0.8, yeah, because what 0.8 is actually, let's say you have developed a network, then nominally the capacity is equal to 1, but because of 10% drop here, you got 0.9, this maybe you get 0.8, this is 0.85, and blah, 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 okay. So in principle, if you apply random linear network coding, you would be able to achieve the min cut of this graph. Okay. So the advantage of such a coding scheme is that you prevent the packet loss to accumulate, and also at the same time you try to you prevent delay from accumulating.
It would be good to quantify.
Yeah, exactly.
All this prevention. Simply because if it's 2 hop and there's already a drop of performance from 0.8 to 0.68, something like that.
Yeah, 0.64. Yeah.
After a few hops, I feel this performance may degenerate.
In fact, we just got a funding from the government to build a prototype using batch code on applied to P2P networks, because it's the same thing. Also, that the batch code can also handle the situation when you have some intermediate nodes which are just helper nodes. They are just there to help. They don't want to decode the whole file. Yeah. Okay, so one thing I would like to mention is that for fountain code, the asymptotic optimal degree distribution actually does not depend on the erasure probability, which is something good. Okay, so you don't need to know the channel condition before you decide on the degree distribution. Okay. Having said that, the actual fountain code being used is actually deviates from the theoretical asymptotic optimal degree distribution. I think for the fountain code that gets into the standard like Raptor Q, they actually obtain the is a recommended degree distribution that is obtained by very extensive simulation in different situations. Okay, so even though the theoretically optimal degree distribution doesn't depend on the erasure probability of the channel, they don't use that one in practice. Okay, so this may or may not be a very big issue we are trying to see. So although the theoretically optimal degree distribution does depend on the rank distribution of the transfer matrix, we see that the dependence may not be that severe. So we are trying to come up with some robust degree distribution, for different rank distributions and see how things work out. Right? And we're also conducting some finite length analysis that's being done by one of my undergraduate project students. And we are building testing systems on multi-hop wireless transmission, and also, as I mentioned, for P2P file transfer systems. Okay, as a summary, Best Code provide a digital fountain solution for networks employing linear network coding. And also, as I mentioned, the more hops between the source node and the sink node, the larger the benefit of Best Code compared with applying end-to-end fountain codes. Okay? And further improvement would include, further development would include proof of the nearly capacity achievement of Best Code in a more general setup, and also design of intermediate operations to maximize the expectation of the rank of H, which is a transfer matrix, and to minimize the buffer size. As I mentioned, if you have a tree structured such that packets cannot overtake each other, then you only need to buffer one packet. But in a general topology, when there are multiple paths connecting the nodes, it's not clear how big you need a buffer. Okay, it really I think that takes a lot more experiment here before we can tell what is a good size of the buffer that one needs to maintain. So that's the end of my talk. Thank you very much.
So, what if you had you pulled a degree out of your distribution that was bigger than M?
Bigger than.
Bigger than your.
It's okay.
So, how do you do the decoding purely in a belief propagation?
Let me see. You get I forgot the details. The degree distribution they use actually have a upper limit. I don't remember exactly how it is being chosen. Okay, I have to go back and look at the details.
It seems like you presented the decoding.
Yeah, I know what you mean. I think probably it was set. The support is from 1 to something which is smaller than M, I think.
Yeah, so that would be a.
That's a very good question.
Strong correlation between M and the degree.
Yeah, that's a very good question. Yeah, I have to look back into the details before I can answer the question.
kind of follow up on Phil's question. So you only try the local decoding within the batch. You never try to put all the equations through the entire file together and try to run Gaussian elimination.
Exactly.
Okay, so then you must lose something there, right?
Let's see. You lose something. I mean, in the extreme case, when you have m equals k and degree equals k, you basically falls back to full-fledged random linear network coding.
It seems like in the media case, you essentially have like 2 layers, right? So within the batch, you try to decode, and then if the batch decodes, then you propagate those back.
Yeah.
But as Phil was asking, if you cannot decode the batch, you still get some rank. If you piece some other ranks together globally, you might be able to decode it, right?
Yeah, so if you restrict your decoding to
what if you stop propagating this? Or they're also, we are looking into the literature of Fanon code. There are many techniques that can be employed for moving forward. So we're looking into that too.
It seems like it could be very fast decoding for most of the stuff.
Right.
And then if you still have any ambiguity left over, then you could try that. You could eke out the last remaining pieces of it.
Right, because in the Fontaine codes, they have the problem if they have cycles essentially, right? So you don't have degree 1 nodes, then you cannot decode. But then you having coefficients here, you don't have to stop there. You can still go on.
Yeah.
Raymond, I have 2 questions. One is on the theory and one is on implementation. So for this network, which is a 2-hop network with some packet loss. And the example you show is with a fixed loss rate.
Mm-hmm.
Now let's assume the loss rate fluctuates across time. My understanding, if it's basically information theory basically based in terms of performance, it should be basically revert to the average loss of the basically network, simply because if you use network coding, you can have infinite amount of memory, right?
Oh, well, the memory doesn't have to be larger than file size.
Basically, you need a larger memory to average out the losses.
No, actually, not quite so for Fanon codes. You don't have to. It does not really depends on the statistical modeling of the channel. Okay, you think about Fanon code. Okay, if I have a blackout, then you don't receive packets during that period of time. If you resume, then you just pretend that nothing has happened. You don't even have to know that something has happened.
My point is, it seems to me that you will, basically, if the rate fluctuates quite a lot, then if your memory is not large enough, you may not be able to take advantage of the higher rate period.
Let me see.
So imagine basically.
I think the issue that you brought up with becomes significant if the packets can overtake each other.
Or if there's significant fluctuation of basically channel capacity.
It shuts off for a long, packet loss goes to 100% for some period of time.
Right.
That's a pretty big fluctuation.
Also, it's like this. For example, in the beginning, the first pipe has full capacity, no loss for half of the time. And then for the later half of the time, the capacity is 0. The second pipe has 0 capacity for the first half and 100 capacity for the later half. Now, to achieve the full capacity, you need the basically memory equal to the whole files to be able to dump all the waters in there. If you do batches, then you will not be able to take basically advantage of the capacity fluctuations.
Well, actually, it is not sensitive to the fluctuation in the sense that all it matters is the number of batches that can arrive. Okay, so you think of this
It's the number of batches you can
yeah, I mean,
remember.
yeah. And you think about this in terms of the encoding graph. If a packet cannot arrive, then you just delete that from the graph. Okay? And because it's random, it actually looks like it looks the same everywhere.
My second question is related to the basically implementations. What if I implement, basically I do the coding separately? So it's this, I mean, the batch code in a sense have two stages, right? The first stage is basically says, I mean, intermediate node, some of the information will arrive at this batch, right? And then you have a second stage, which is this M, basically is coding within batch.
Right.
Now, let's say we are operating on a packet basis, so the overhead on each packet is relatively low. So, I mean, can I simply, basically, I mean, during the second stage, I will try to decode what the first stage is.
Okay, so you mean the intermediate nodes try to decode, or
No, the end nodes try to basically decode.
Okay,
it.
let's go back to this picture so that we can make reference. Okay, so at what stage are you trying?
So what I'm saying is this.
Oh, I'm sorry. This is not the right picture. It's not the right picture. Yeah, this should.
I need a two-stage graph.
Okay, this right?
So it's like this. So the first stage, for example, the intermediate node basically hold the information.
You mean here?
Yeah, here says.
Oh, no, these.
To bring.
Yeah, these are. Okay, for this case, this arrives at the intermediate. This arrives. This doesn't arrive.
Yeah, this doesn't arrive.
Yeah.
Yes. So I basically put that patterns into the message.
Put that pattern into the message. I see. Okay,
so let's say I use a binary vector says, okay, here's the packets which arrived.
Okay, I see. So yeah. Okay, so this is fixed. The size of this is fixed, and then you tell the downstream that the third guy actually had not arrived, and I'm only taking random linear combination of the first two guys. Okay, so yeah, and you're trying to see whether this can help.
Well, I mean, whether this scheme is simpler.
Whether this scheme is simpler, but how are you going to make use of that information?
Let's say this can be transmitted as overhead.
Overhead. No, but I mean, but in what way is this information useful to those downstreams?
So the downstreams only need to know how many valid packet is in that batch.
Okay.
And simply design basically a code which is equal to the size of basically equal to basically be able to decode that batch. So for example, the batch here is size K. Okay. Now
let's stick with M. Okay, this batch is M. Okay.
M. Okay. Then I mean after the first stage, the number of packet arrived is anywhere between 1 to n.
Right.
Right. Okay. I only need to basically get the information of what packet is arrived in this n, the n bit vector.
Mm-hmm.
Send to the basically receivers. The receiver basically have a rateless code to recover exactly the number of packets received during the intermediate node. And when it received, it basically says, okay, I mean, I don't need any more code.
Mm.
So here, of course, the receiver is, in a sense, act to the intermediate. Every, basically, of this K packet.
Okay, I'll think about it more carefully. See whether we can, take advantage of this. Thanks for your input.
So I want to go back to that question, why you choose constant m?
Why choose constant m? Because well, in this case, for example, if you only need to store m packets.
Yeah, I think so. The main reason is for the intermediate nodes buffer, right?
Right.
But if you set m equal to d, then you kind of avoid what Felix mentioned, right?
Well, it really depends on the application. For example, in the current generation of P2P system where there's no helper node, so everybody wants to have the same whole file anyway, so buffering is not an issue. So yeah, for some application it doesn't matter, but this is mainly for helper nodes or some like a router where you don't want the buffer size of the and the router to grow with the file.
Well, I guess if you've already got D, an upper limit on D, and you already pick M to be.
Well, but if there's an upper limit on D, M can still be big, right?
Yeah, but I guess so you pick M to be bigger than the upper limit on D. But maybe if you pick a D that's smaller than that upper limit, then maybe you can just use a smaller batch.
The size of M cannot be too small, otherwise you cannot get the benefit of random linear encoding. Yeah, but actually what we find a little surprising is that M can be chosen to be quite small, and yet the result is already exceeds Fanon code.
Okay. Thanks.
All right, thank you very much.